In this video, I'm going to show you how to find and classify discontinuities of a function and to justify those discontinuity classifications using limits. So here's the function that we're investigating. It's f of x is equal to 2x plus 10 over x cubed plus 3x squared minus 10x. Now before we dive in, let's do a brief review on the three kinds of discontinuities. A jump discontinuity occurs at a point, in this case x equals c, when the limit approaching c does not exist. From both sides you reach different values. The two roads don't meet in the road and bridge analogy. And as a note, these are typically found in piecewise functions, although not necessarily always. Removable discontinuities have the following feature. The limit exists, which is to say in this particular example, the limit approaching c of f of x is equal to b. However, the function at exactly c is not equal to b. In this case, the function evaluated at c is undefined, but the function at c could be anything except for b, meaning you could have a value up here somewhere. So in layman's terms, the limit exists. And finally, an infinite discontinuity means that the limit as you approach c from either direction, from the right or from the left, will give you either positive or negative infinity as an output. So this is another way of saying a vertical asymptote. So let's actually find the discontinuities here. And the way to do that is to manipulate the function or factor it or sort of see its different forms and make comments about those different forms. So looking at this function, I observe that I can probably factor the top, and maybe that'll cancel something. If I factor a 2 out, I have this right here. The bottom's a little bit trickier. I have a common term x, so I'm going to factor that out, and I'm left with x squared plus 3x minus 10, and that furthermore factors into, let me just bring this here. So I have that x out, and then that would be, let's see, to get 10, that could be x plus 5 and x minus 2. So I haven't done anything except for rearrange this function and reveal its different forms. I can now rewrite it a bit by using some cancellations. So I recognize the common term on top and bottom, and that's a dead giveaway that the value that I've just removed from the function, which is to say the value that would make it a 0 on the bottom, which would be negative 5, that is probably going to be a removable discontinuity. So I'm going to write x equals negative 5, removable. The reason I have a question mark there is I haven't justified it yet, but it's probably a dead giveaway that it's going to be. And if I simplify my function, I'm left with 2 over x times x minus 2. And if I look at what is not able to be removed from the bottom, I'm left with two values. One of them would be x equals 0. That will make the bottom equal to 0. And the value that makes the bottom equal to 0 here is x equals 2. And if you're not sure what I'm doing, all I'm doing is I'm solving this simple equation of setting the bottom equal to 0, because you're not allowed to divide by 0. Another way of thinking about these values down here, which of course in turn yield these values, are you can think of these as essential discontinuities, that's a term that's sometimes used, or non-removable discontinuities, which means they cannot be removed. Those are sort of synonyms for infinite discontinuities. But the terminology we typically use is an infinite discontinuity. So I'm going to write, are these two values infinite? We have to justify whether or not they are. So all I've done so far is to take the original function, factor it, and have a critical eye as to what it is I'm removing if I do remove something, and what it is I'm left with once I have factored it completely. So now to justify our classifications. Is x equals negative 5 really a removable discontinuity? Let's find out. Remember, removal occurs when the limit exists, but the function is not actually equal to a value at that point. Now you'll notice I cannot plug negative 5 into the original function. I get 0 on top, and for reasons you can see, I get 0 on the bottom as well, and 0 over 0 is indeterminate. So the function at negative 5 is definitely not a value. The question is, what is the value at approaching negative 5? So to justify whether or not x equals negative 5 is a removable discontinuity, I'm going to take the limit approaching negative 5. Oops. Approaching negative 5. And I could use the original function, but I know I can't plug -5 in, so I can't use direct substitution. Let me fix that arrow here. So I'm going to just go ahead and use the simplified versions. What we had after we did all the factoring was this. Let me go back a slide. This right here. So I'm going to plug -5 into this using direct substitution and see what that gives me. So that'll give me 2 over -5 times -5 take away 2 will be -7. That'll give me 2 over 35, which is a number. And that means that my two roads, so to speak, the function approaching -5 from both directions will give me 2/35, but the function at exactly -5 is undefined because I cannot plug in -5 into the original function as it was provided. So the fact that I took a limit and found an existing value tells me that x approaches equals -5 is in fact a removable discontinuity, and the justification is below. I took a limit and it exists. I have two candidates for infinite discontinuities, and those are, going back here, x equals 0 and x equals 2. So I'm going to justify each of those individually. So let's first start with x equals 0. Is x equals 0 an infinite discontinuity? Well, to justify that, I need to take the limit approaching 0 of my original function, of my cleaned up version of the function, which is this guy right here. And if I try that, I'm going to end up with 2 over 0. So this is a common mistake people will make. People plug it in, and they get 2 over 0, and they say that's equal to infinity. Keep in mind, you cannot divide by 0. That's a hard and fast rule in math. We sometimes get away with it in math, in calculus certainly, by approaching 0, but you cannot divide by 0 itself. So to fix that, and this is sort of the rationale behind why we do this, we have to take a one-sided limit. So I can't factor this anymore. The next sort of tool in our toolkit is to take a one-sided limit. So I'm going to choose the positive side, but I could choose negative as well and get a valid answer. So this is the correct route to go, is to choose a one-sided limit. So 2 over 0 from the right, and then 0 from the right, take away 2. So remember, this is sort of a placeholder for positive 0.00001. Let's see, 0 from the right, take away 2 would give me some sort of negative value. I'm not too concerned with what it is, because I know that as soon as I multiply it by a very small number, like 0 positive, it's going to become very, very close to 0. So that'll give me 2 over 0, but since it's a positive number times a negative number, that's going to be a negative result. And this time I'm not dividing by 0, I'm dividing by a very, very small number that's a little bit less than 0, and since the top is positive and the bottom is not, I'm going to get a negative infinity. And since I approached a finite value and my function exploded to give me a negative infinite result, this justifies that at 0 I indeed have an infinite discontinuity. I also suppose that x is equal to 2 was also an infinite discontinuity, so let's justify that if we can. Let's take a one-sided limit at 2 and see what that gives us. So I'm going to choose from the right again, 2 over x minus 2. So now I plug it in. Let's see what we get. 2 over 2 from the right, 2 from the right, take away 2. Here I have to be a little more precise. So this is 2 from the right. 2 from the right, take away 2 is going to give me 0 from the right, because I have a bit of crumbs left over. 2 and some crumbs take away 2 leaves you crumbs. That gives me a positive infinity on the, positive 0, a bit more than 0 on the bottom. The top and bottom are both positive, and the top is a number and the bottom is a very, very small number, so I'll get a positive infinite result. And because I approached a finite value and my function exploded, this is indeed an infinite discontinuity. And the justification for each one is below. So to review, to justify a removable discontinuity, well, first of all, to identify a removable discontinuity, factor your function and see if you have any cancellations. To identify an infinite or essential or non-removable discontinuity, factor in whatever you're left with in the bottom. Producing zeros will be your candidates for infinite discontinuities. And to justify, show that the limit exists for removable, and show that the limit is infinite from one side for infinite. Hope this helps.